Good afternoon. First, I am going to introduce the topic and the motivation behind this study, then the applied methodology and the results. Bridges are strategic points in the road network because of the severe consequences of their failure or closure to traffic. So, measures must be taken to prevent these structures from deteriorating to the point where they compromise the safety of users or require diversion. However, various agents such as harsh environmental conditions, increasing traffic volumes, vehicle collisions, aging, and deferred maintenance can lead to the gradual deterioration of bridge components over time, potentially compromising their functionality. Symptoms of such gradual deterioration arise in the form of surface or subsurface defects, as we can see in the photos, such as cracking, corrosion, spalling, delamination, and scaling. And if neglected, might lead to catastrophic failures in terms of human life, social, environmental, and economic impacts. As such, planning bridge inspections is important to assess the condition state of different bridge components by field inspection or deterioration models that further help highway agencies to optimize their intervention plans. And most importantly, the collected data will help in forecasting future deterioration conditions and future funding requirements. However, current practice faces some challenges, including lack of data or difficulties in collecting data from different sources and formats. Inspection data are of unstructured nature, buried in textual inspection reports without being effectively utilized. And the current models tend to focus on abstract data related to bridges and the crossing routes, such as construction year, geometry, annual average daily traffic, and so on, while neglecting inspection and the defect-related data. To tackle these challenges, the main goal of this paper is to create a structured and comprehensive data repository that can be used for further processing and developing asset management tools for bridge infrastructures. The proposed methodology comprises two phases and was applied on a case study of bridges in Quebec, Canada. The first phase is a three-tier method designed for data acquisition and compiling that included acquisition and analysis of bridges main dataset, web scraping of bridge-related data from Ministry of Transportation websites, information extraction from bridge inspection reports. The output of this phase is a structured, comprehensive data repository ready for further analysis, processing, and modeling steps. The second phase intends for data processing and text mining of inspection comments. This phase enables the analysis and the visualization of the important information related to different types of defects in bridge decks, which is the focus of this study. The first tier of the first phase involves obtaining the primary dataset of structures from the Quebec datasets website, which is then stored in a local data repository. The data is then subjected to preliminary preparation techniques such as integer encoding to make it suitable for subsequent processing and modeling steps. However, the main dataset doesn't contain important pieces of information which are available in other sources. For example, bridge dimensions including length, width, and area, inspection data including general condition index, last and next inspection dates, and the route characteristics including average annual daily traffic and the percentage of trucks. This information, as we can see, is available separately for each structure, which require the web scraping to be collected correctly and most importantly in a timely manner. So the web scraping using Python was applied and the collected data were cleansed, prepared, and added to the main data repository. In addition to these data, bridge inspection reports contain text information related to the structure and the different types of defects in each bridge component. To collect and structure this information, the third tier involved the utilization of rule-based information extraction techniques to extract these pieces of information and transform them into a structured format. Last but not least, the second phase applies different text mining techniques to get insights into inspection comments extracted from inspection reports, including the most common defect types detected by inspectors, the association or co-occurrence between different types of defects, and finally, common language and comments used by inspectors in order to standardize this language and determine the severity levels associated with these defects. After implementing the proposed methodology, the results can be summarized into three major outcomes. First, a structured data repository including all collected information, as we can see. This is a part of the variable view of the repository using SPSS. It includes variable name and the type, if it's numeric, scale, or ordinal, or nominal. A label to describe the variable in detail, and also the values of each variable that enable the mapping of different values, as we can see in case of root class. Here is also parts of the data view of the repository that show how the data is structured, including here inspection comments and the different defects related to different bridge components. Second, insights and analytics related to inspector comments, including absolute and relative frequency of different defects. Cracking and spalling are the most frequent types of defects detected by inspectors. Association or coexistence of defect was also investigated that showed spalling is highly associated with the presence of cracking and delamination. This result was very important to verify the outcomes from information extraction and text mining, and also to identify the common language used by inspectors. This common language was then extracted and transformed into standard format. For instance, if the inspection comment include cracking greater than 15 millimeters, then the cracking severity can be standardized to severe and so on, using the shown table. The third outcome is a defect-based Bayesian belief network used to determine the impact of different defects on the overall deck condition probability. Different defects were considered as parent nodes with 4 states: slight, moderate, significant, or severe, while bridge deck was considered a child node with excellent, good, fair, and poor states. The prior probability distribution of each defect was determined from the text mining results, and the conditional probabilities were quantified using the maximum likelihood. For conclusions and future research, the current study showed that the development of reliable management tools usually impeded by a lack of data or difficulties in collecting and organizing data from different sources and formats. However, the implementation of an integrated approach involving web scraping and information extraction technique is required for automated collection of bridge data and evaluation of deficiencies in a timely manner. Also, data buried in inspection reports should be analyzed and incorporated in bridge deterioration models and management tools. The next step of this research includes adding a time dimension to the lastly developed Bayesian network to transform it to dynamic Bayesian belief network that help in determining the deterioration over bridge components over time.
Thank you very much, the speaker, Dr. Omar.
Thank you so much for your attention. I hope I had the opportunity to make it and be in person in this conference. However, if you have any question, please feel free to forward this question to my LinkedIn page or my email address. Thank you so much again.